This week, we're going to look at a way that you could use MetPy in the classroom to help your students understand the concept of scale height. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week, I want to show you a way that you could use MetPy and Jupyter Notebooks in your classroom, and that's by talking about the concept of scale height. We generally introduce this to students in thermodynamics, though planetary scientists also work with scale height a lot too. Generally, we write some equations on the board and say something to our students about it being the E-folding depth of pressure or density in the atmosphere, and move on to the next concept. But I found that a lot of students don't really get that concept initially, and it really helps to view things on a graph and be able to play with some of the numbers. And they may not want to do that by hand, punching things into their calculator, but with MetPy and using Python notebooks, we can make some really quick examples and help our students understand scale height. So since we're going to be doing some computations, I'm going to import NumPy as MP, import matplotlib.pyplot as plt, import metpy.calc as mpcalc, and from metpy.units, I'm going to import the units registry. So the first thing that I want to do is use the scale heights function in MetPy Calc, and we might tell our students something like, well, we generally think of the scale height of Earth's atmosphere as something like 8.5 kilometers. And they see in the equation that there's a mean temperature involved. So, well, what's the mean temperature of the atmosphere assuming a scale height of 8.5 kilometers then? Well, if we look at the scale height function, it actually takes a temperature at the bottom and temperature at the top. Notice it says that this assumes dry air, but if you use virtual temperature, you could account for moisture. There's some great homework problems in there. But let's start out and let's just take a guess. Let's say we use standard temperature at the surface, and we don't really know what height we're thinking of temperature at here. So let's start, I'm just going to say 0. And close the parenthesis. And that gives me a scale height of 8.36 kilometers. So is warmer or cooler mean temperature going to make this certain height, this E-folding height in the atmosphere, taller? Well, we can experiment. I can try -5. Okay, that went down. What about 10? Okay, so 10 gets me pretty close. So what's the mean temperature that we can assume for the atmosphere? Well, it's the mean of those, 17.5 degrees Celsius. Again, there's a lot of things you could discuss with students there. But now we've used the scale height function, we sort of started building an intuitive feel for whether higher or lower mean temperatures make the scale height go up or down. But I want to make a graph and actually show what atmospheric pressure is doing with height and where the scale height is on that plot. Because our students know that the atmosphere, the pressure and density decrease logarithmically, and that might start giving us some inclination about why we use E in the E-folding distance here. But what is the E-folding distance? Well, we can start out with that. 1 over E is 0.367. So we can think of it as where about 37% of the pressure is above us and everything else is below. Okay, so let's do that calculation now. And again, the great thermodynamics problem to look up or even derive that the pressure at an altitude or pressure at a height is the surface pressure times E raised to the minus height divided by, guess what? The scale height of the atmosphere. This is a really great way to show that you can take the equation for scale height and plug it in here, but it's a great example of why you might use a scale height. Okay, so I'm going to create a function, pressure profile. It's going to take a top height, a scale height, the number of points that I want along that curve. I'm going to set that to be a default of 500. And a starting pressure, which we'll set to be 1013.25 HPA. Put a quick doc string in here. Calculates pressure profiles for heights, returns profile, heights, and DZ, our change in height. The height, I'm going to use lin space for now. You could use log space here if you wanted. I'm going to start at 0. I'm going to go to top height, and I'm going to do that in points. Then I'm going to return the starting pressure times e to the minus z over scale height. The heights, and then dz, this might be useful for us to know how many meters are in between each point when we're using in points. So we can say the pressure, the z, and the dz, call our pressure profile function. Let's go with 40 kilometers and a scale height of 8.5 kilometer. And make a plot. Okay, so because we have units attached, matplotlib is putting units on the plot for us, so we don't really need to add any additional labels. And we see that as we're going up in height, the pressure is decreasing logarithmically. Great, that's what we expect. But now I'm going to put some markers on the plot here. A horizontal line, and that horizontal line is going to be at our E folding height, or the surface pressure, which we said we use the default of 1013.25 divided by E. I'm going to make that a black line and dashed. Okay, and now we will copy that, make a vertical line. Instead of y equals, now it's going to be x equals. And I'm going to put that at our scale height, which was 8.5 kilometers. And we see those lines intersect right on our pressure curve. Using notebooks like this is a great way to let students explore different concepts and get an intuitive feel. For example, well, how much does the mean temperature change the scale height? Well, we could do a quick investigation of that. We could set a temperature range from 0 to 24. Use the scale height, start at 25 at the surface, and temperatures, assign our units. Oops, a range. We'll make another plot. And this time let's scatter plot. And there we see that as we change the temperature of the top part of our layer, so we're decreasing the mean temperature, the scale height decreases, and over a range of about 25 Celsius, We're changing from about 8.35 kilometers to 8.7 kilometers. So again, this is just a good way for students to start getting an understanding of, well, how much does scale height change? You could calculate scale height on another planet using different constants and compare that to Earth and talk about what that means for the atmospheric dynamics and for the atmospheric thermodynamics. I hope that you found this useful, and I'll see you on next week's MetPy Monday.